Hello students, and here we are again. Here's organic synthesis number 1, worksheet number 1, problem number 2. We're in this case converting this one to this one. When we inspect this particular exercise, what we see is that the carbon skeleton is pretty obviously the same. All we're doing in this case is moving functional groups. So let's take a minute and look at the functional groups. One of the things you'll notice is you have a double bond up here, and it seems to be missing up here, right? And we're also going to be making some double bonds in a minute later. So we don't want to actually have double bonds two different places where we want one and we don't want the other. So I'm going to go ahead and add H2. Oops, not H2O. H2 in the presence of our catalyst, palladium or platinum, MEA. All right, so that bond goes away. Now I want to move this iodine from here over here, right? Make sure you read the directions for this one. Here's a case where it's going to require a couple of different reactions, but we're not going to get the product in 100% yield. That would be the goal, but in this case it's just not possible. So we're going to do the best we can with that. So make sure you read the directions for number 2 here. All right. How can I start moving this iodine in this direction? We basically have to walk it over there. So we could do substitution, right? But that would just stick something else in this particular case. So we're actually going to do elimination, right? We can use, if we wanted to, OH minus. OH minus is a good base, and that will do elimination. But because this is secondary, we may also get some substitution. So we're going to use instead a super powerful base called LDA. LDA is talked about a little bit in your giant table of organic reactions. It's down here in the bottom under E2. The cool thing about LDA is lithium diisopropyl amide. So this is the amide part. Amide is one of those things where, yes, this is also an amide. A-M-I-D-E. So the word amide in organic chemistry unfortunately refers to two very different things. It refers to this functional group, which that's not what we're talking about right now. And it also refers to nitrogen with a negative charge. So this is also an amide. So this is lithium diisopropyl amide, or LDA. You can just call it LDA. I'm not going to ask you to draw the structure about it. But the cool thing about LDA is because it has these big bat wings, there's a lot of steric hindrance, and LDA cannot come around and do substitution. It can't do SN2 at all. So it will do sort of elimination, but not substitution. Hold on, my lights just turned off. I'll be right back. All right. So LDA is like an awesome, cool, powerful base, right? It's like an uber awesome base that doesn't do substitution, it only does elimination. So when we add LDA, we're going to do E2, bimolecular elimination. This is going to be eliminated, and like with all eliminations, we're going to form a double bond, and we're going to follow Zaitsev's rule. Zaitsev's rule means the double bond is going to tend to form in the more substituted position. So here's our Zaitsev product. All right, check. Guess what? We can make that iodine come back, and we can make it come back someplace else. If we add HI, that's an MEA reaction. We're going to get hydrogen on one side and iodine on the other side. The Markovnikov product is going to be this one. Aha! So notice we moved the iodine from here to here in 2 steps. We did elimination and then MEA. Well, that's good. Let's try that again. What happens if we do elimination again? More LDA. In this case, if you wanted to, you could just add hydroxide because this is a tertiary position, so you're not going to get any substitution at all. So one or the other, not both. Now, here's where things get a little dicey because Zaitsev's rule says in elimination, we're going to get the more substituted position. This one and this one and this one are all equally substituted when it comes to deciding where to put that double bond. So we're actually going to get a mix of products. some of them are going to look like what we just had, right? When the double bond is either here or here, that's what we just had, right? That was actually after step 2, right? So the bummer news is we don't want that. The good news is we can just recycle that. If we happen to get some of this or some of this, we just go back to step 2 and we keep going. We will also, though, make some of this. And now we're close, right, from going to here to here. The only thing we need to do is we need to break this double bond, and we need to add the more electronegative element in the less substituted position. So that is electrophilic addition, but that's not the Markovnikov flavor. You remember that we did learn about one other flavor of electrophilic addition, and that is the anti-Markovnikov flavor. So if you check this out, this is the middle of page 2 on your big giant free gift. If you add, in this case, HI and some sort of radical initiator, like benzoyl peroxide, you'll get the anti-Markovnikov product, the one that looks like that.